Hello and welcome to my presentation, Sun, Wind and Water for Hydrogen. My name is Dr. David Blechman and I'm professor at California State University, Los Angeles. This is our first slide that developed. The graph was developed by Lawrence Livermore National Laboratory, and it basically gives us a map of energy consumption in United States. And if you look here on the left, you can see that majority of the power in United States is produced by natural gas, then coal, and petroleum, which are fossil fuels. The share of solar and hydro is very low, and we are approximately 8%. You can see that the total is almost 100% or 97.3 quads, but we can imagine that it corresponds to percentage points as well. So over 75% is produced by fossil fuels, and we realize that energy production from fossil fuels is not going to be forever, because fossil fuels are finite and it gets harder and harder to get it out of the ground. There are political, economic and other consequences that are happening around the world due to energy trade. And so becoming more independent with solar and wind will be a really good and strong solution. In addition, we got to realize that we are burning let's say, over 100 years, we're going to burn through fossil fuels that were forming over millions of years. So over millions of years, CO2 was captured from the atmosphere, and now we are releasing that process back into the atmosphere, which is heating up because of the amount of CO2 that is being absorbed in a very, very short period of time. And we can see significant climate shift taking over a short period of time. So this is to our advantage to now capture solar and wind power and use that as our solution to this problem, climate problem, and finite amount of fossil fuels. So how we're going to do it with wind? So with wind we have opportunity to capture it with wind turbines. And here on this graph you can see a schematic of a wind turbine with a circle which approximates the circle of the rotating blades. And we can't stop and capture 100% of the wind power. Actually, it's going to work like a wall. If we stop wind will stop going into the wind turbine. So we need to let some of the wind pass through. And so what it comes down to that 2 and 3 blade wind turbines, which are the most efficient, we are going to have about 50%, 45 to 50% capture efficiency when there is a good wind. Also, in order to get a good wind, we need to align our wind turbines along the prevalent wind. So it's a rows of winds here. And so it shows us where the wind is blowing in that location, and that's how we are going to locate our wind turbine and estimate how much it will produce and what would be the payback time. Also, this circle implies, so the bigger we build these wind turbines, the more wind we capture. So you can see there is a trend to build larger and larger wind turbines. And here is an example of a wind turbine. So the company is a Nordex on the left, and on the right you have an actual picture of a wind turbine by General Electric installed in Ireland of the shore. So what I would like to show you on this slide, that the wind turbine technology is not impossible. It's actually very good with very good engineering. It's a relatively straightforward process. So we have blades. Blades are engineered like airfoils on the airplane, so there is a specific design to capture wind really good. Also, we have here is a shaft, main shaft coming from the rotor into the gearbox, and gearbox will speed it up 20-30 times and spin it faster. And then out of the gearbox right here in the middle, which is very high quality machinery involved, and then it goes into the generator, and that generator will produce electricity that we can actually transmit by the through the transmission lines to our applications. However, how wonderful the wind is, so we can put it anywhere, but the solution is to put it where we have the most wind, so it pays off quicker. Here's a US map, and where we have white regions, it's not a lot of wind. Light blue regions are medium quality wind that you can produce. However, Dakotas is very windy. Also, Michigan or Great Lakes are quite windy, and we can collect some of the wind there. But in reality, if you are producing wind somewhere here in these regions or in these regions, then you need to transmit that electricity to a variety of your customers. So, and that goes over the long line. So that's why we don't have a lot of proliferation of the wind energy in the United States yet, but hopefully we can continue capturing and building and investing into transmission lines. Another aspect of the wind power that it's intermittent. Here I have some data for European countries. Denmark produces quite a bit, actually the most than even the whole Germany, because Denmark has a really good strong winds. But even in that country, its production is intermittent, so you really can rely only on this like 0.2 on the bottom, but the rest is unreliable. It could be up and down or more or less. So at some point what happens is we are relying on this production, but the rest we need to sell a little bit cheaper. So that's kind of one of the issues with the wind power, that it's intermittent even if you can produce enough on some days. So in a very significant fluctuation. Now let's switch to solar. Here is a solar map for entire world. And this you can see that the northern regions or polar regions like northern Europe doesn't have a lot of solar potential over the whole year, so investment into solar there are not as good as investment, for example, in North Africa with Sahara. And so we can produce electricity in Africa and then transmit that to Europe, and hydrogen could be a really good carrier of that energy. Australia is planning to become a world source of hydrogen. Right now it's a really good source of coal, but they're hoping to transition with the solar production of hydrogen or other forms of fuels converted from solar in Australia. Also Southern Americas also have a high capability of producing lots of solar energy, and of course United States, especially southern states, are quite capable of producing significant amount of solar energy. You can also see Asia, Middle East is especially capable of producing, India and Middle East producing solar energy if needed. All right. So this is a very encouraging slide. Even though in the United States we are not producing a lot of solar energy yet, around the world the production is growing exponentially, so it's growing really fast. And when I accidentally I teach photovoltaics class, and in the photovoltaics class I have when I started teaching it was right there, and you can see over 15 years that I've been teaching it. It has grown so much, and I'm very proud of those results. But even solar energy is prone to some problems. So let's look at this slide. On this slide, we can see that the energy is produced only over a period of a few hours. So this is a Cal State LA installation. This is our own data from Cal State LA, and you can see that the production is over several hours, and during the day there is a peak, and then it goes down really quickly. And the first day is good, second day is good, but then on third day it was very cloudy, as you can see, and we produced probably only half of the normal day. Then the fourth day is good here, but then this one is truncated, probably clouds came in and we didn't get this second half. So relying on solar is also problematic, so we need to store some of that energy. Particularly in California, but I would say many countries would experience that as well. We have so-called solar power duck curve. What it means that during the day, so our energy consumption drops, or production. So if I have a power plant, for example, coal, if I have a coal power plant and I run it so that overnight, so I'm running it, well, if not coal power plant, but some other plant, nuclear power plant, something I'm running to produce electricity, and during the night it's all good, but and because of the solar during the day, right? So solar is now playing a role. The energy needs are dropping. And so my plant, I cannot ramp it up and down so quickly. It's not good for thermal production or thermal-based power plants to run up and down. Nuclears don't want to run up and down. They just want to hum constantly, right? And so here we go. There is a overproduction of solar. What do I do with the overproduction? I need to store it. But then what happens after that? Sun disappears, and now suddenly I have to produce that much power to still run your air conditioners, right? So I need so-called reactive power. What could be reactive power? Fuel cells could be our reactive power, but we are still using turbines. So gas turbines are our reactive power. And so here in California and Los Angeles, we are working on converting our turbines and being able, well, actually we'll change for new turbines, but the new turbines will be able to run both on natural gas and on hydrogen as more hydrogen will come in. And now this gap will be covered by hydrogen as well with gas turbines and fuel cells. But overall, this shape we are calling a duck curve. And that is a problem that we are overproducing electricity, solar electricity during the day, but by the evening it's a big problem. All right, so here we go. Cal State LA has its own electrolyzer hydrogen station. So this is our electrolyzer big container. In this container we have fuel cell stack. It's kind of running backwards, so it's electrolyzer stack. And we use electricity from campus microgrid that is fed by solar, but again, solar is only during the day. And then we are taking water, H2O, split it into hydrogen and oxygen. And then in order to produce 1 kilogram of hydrogen, we need 9 kilograms of water, and we are producing 8 kilograms of oxygen and only 1 kilogram of hydrogen. So water is something that we need to be not concerned, but it's in many locations it might be a problem converting electricity to hydrogen because you need a clean water source for that. And here is a really interesting graphics that I borrowed from Ballard. We also have a similar graphics which I shared last time, produced by our students. But what we covered here is production from wind and solar into electrolysis. From electrolysis, it will be stored in hydrogen, and then when we need it, we can use that hydrogen for transportation, or we can use fuel cells. For example, here is a Ballard fuel cells or turbines to combine with the grid electricity for our needs. And that's the main message. And so this is the end of my presentation, and I hope you learned a little bit more about sun, wind, and water for hydrogen production and for hydrogen economy. Thank you.